Hello, today in this video we are going to talk about the radius of convergence for power series and Taylor series in general. So let's start with the most simplest case, which are geometric series. When do these series converge to a finite number and not diverge to infinity, blow up to infinity? For the condition in which this series, geometric series, a plus a times r plus a times r squared plus dot 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 to infinity, to converge to a finite number, the absolute value of r has to be less than 1, uh, so that as limit n goes to infinity, r to the n equals 0. If that's the case, you can multiply Sn by r, which you get these sum of series here. And if you minus Rsn from Sn, all these terms goes away because they are the same. And the last term, the ARN, a to the Rn, AR to the n, becomes 0. So you can just ignore that term. All you get is just Sn minus Rsn, it becomes A, and Sn you get simplify. You can simplify it and you get A over 1 minus R. So for example, if the geometric series is 1 plus 1 halves, 1 quarter, plus 1 eighth, plus dot dot dot, so on, the A here is 1 and R is 1 over 2, 1 halves. So if you plug it in there, plug it in this equation here, you get Sn equals 2. So the condition in which the geometric series converge to a finite number is the absolute value of r is less than 1. Now let's look at the power series and the Taylor series. The power series looks like this on the right hand side here. It looks similar to the geometric series, but it has a coefficient C0, C1, C2, which they don't have to match each other. They don't have to be identical. Whereas in the geometric series, they were just A and they were just identical numbers. In the power series, they don't have to match each other. The Taylor series is similar to the power series, but fx, the original function we want to know, can be expressed in these terms here. If you expand it about x equals a, you get fa, and you can get the coefficient, and x minus a to the 1 power, and x minus a to the second power, and dot dot dot, so on. These are just coefficients, c1, c2, c3, etc. So they are very similar to the power series. And the last video, we actually derived the e to the x, sine of x, cosine of x, and their Taylor series expanded about x equals 0. So we did that last video. We actually derived from scratch the Taylor series of these functions here. Uh, but we didn't mention about the condition in which, on the right hand side, the Taylor series, does it always converge to the original function, or does it blow up to infinity, or there's a mismatch, so it diverges from the original function? We didn't talk about the condition in which it does that. Because actually, if you look at the fourth equation here, ln of 1 plus x, the right hand side Taylor expansion of expanded about x equals 0, you get this Taylor series here on the right hand side, but it has a condition in which this Taylor series diverges from the original function other than the condition in which the absolute value of x is less than 1. So for example, if you plug in x equals 2 on the right hand side of the equation, the Taylor series, it doesn't match the original function ln of 1 plus x. But in here it does match. So what is the condition? How do you get the condition for which the series to converge to its original function and doesn't blow up to infinity or not? The test you do is the ratio test, which is this equation here. It may seem very complicated, but if you look close enough, this is Cn plus 1 is just the n plus 1th coefficient. and this term is just the n plus 1 power. So all this is saying is the n plus 1 term over nth term, and put the absolute value of that and set n go to infinity. That has to be less than 1 for the series to converge to its original function, or just doesn't diverge and converges to whatever you want to know. So this equation, if you can simplify it to this equation, you shuffle it around and you get the simplest, the more simple version of that equation. But that's not important. All you need to do is calculate the this term here, n plus 1 term over nth term, and set that less than 1 as n goes to infinity. You have to calculate the ratio test yourself. So, for example, if you have a series like this, 1 plus 1 half, 1 third, 1 quarter, the nth term of this is 1 over n. So you might think as limit n goes to infinity, the nth term goes to 0. So you might think the series converges to a finite number and doesn't blow up. But you have to do the ratio test in order to know the truth. So let's do the ratio test of this series here. And you get the n plus 1 term is 1 over n plus 1, right? Here. Over the nth term, which is just 1 over n. If you simplify this, you get n over n plus 1, which if you put limit to n equals n goes to infinity, this term here equals 1, which you know is the condition for which the ratio test to be satisfied is less than 1, not 1, not equal to 1. So you can learn from the ratio test that this series actually goes to infinity, doesn't converge, diverges. To see that it actually does goes to infinity, you have to, there's a simple trick you do. Put a bracket around here, and if you put a bracket around here, 1/3 is greater than 1/4, right? So there are two of them, which equals 1 over half. Similarly, all these terms in front here, these threes, are greater than 1/8 respectively. So there are four of them, which equals to 1/2 also. So if you keep doing this, you have 1/2, 1/2, 1/2, 1/2, 1/2 to infinity. If you plus 1/2 to infinity times infinity, that's just infinity, right? So this series here actually goes to infinity. And we can know that by doing the ratio test. Now let's do the ratio test on the genuine Taylor series we derived last time. E to the x expanded about x equals 0. You get these Taylor expansion on the right hand side. So let's do the ratio test on the right hand side and see if it what's the condition for the right hand side to converge to its original function. So you get the nth plus 1 term and you get the nth term, and you plug it in this equation, this formula here. The nth plus 1 term is just x to the n over n factorial, and the nth term is just x to the n minus 1 over n minus 1 factorial. And if you simplify that, you get this. And because n goes to infinity and n is a positive number, you can just multiply and simplify this out. You get absolute value of x less than n, but n goes to infinity. So the absolute value of x less than infinity, if this is satisfied, then this on the right hand side, the Taylor series, does converge to its original function. So the radius of convergence, or the condition in which x has to satisfy for the Taylor series to converge to its original function, is just from minus infinity to infinity. So that's all finite number of x, just all finite number of x. So that means all finite number of x satisfies the Taylor series Taylor expansion of e to the x to converge to its original function e to the x. This implies if you expand it about a certain point, x equals 0, for example, x equals 0, and you know all the information around that point, for example, f0, f prime 0, f double prime 0 to f nth prime 0, you know all the information around here, x equals 0, you can construct e to the x, the original function, by the Taylor series here, summing up all this here, Taylor series, and you can get all values of e to the x with any x. There is no condition in which if x is greater than this number, this Taylor series doesn't converge to this original function. There are no conditions. But as I said before, ln of x plus 1, which has a Taylor series on the right hand side, expanded about x equals 0, the Taylor series, this series doesn't converge to its original function ln of x plus 1 when it is outside of the boundary of the condition x greater than minus 1 and less than 1. So if x is 2, it doesn't converge. This on the right hand side doesn't match the left hand side equation, left hand side function. So graphically, you can visualize that the ln of x plus 1 here is this function here, and it goes to minus infinity at the point x equals 1. So if you expand it about the x equals 0 point, x equals 0, you have all the knowledge of the function here, infinite knowledge and information about the graph here. It doesn't match this function you get from this Taylor series you get from here doesn't work if you plug in x equals 1.5 or 2 here. It doesn't match the original function. It diverges. The Taylor series. This green graph here is the visualization of the Taylor series we get. This doesn't match the original function, right? So it diverges from its original function. This 2 here diverges from the original function ln of x plus 1. So if you do the ratio test, the n plus 1th term of the Taylor series of ln of x plus 1, you get the n plus 1 term here, n plus 1 term. You get n plus 1 this here. And the nth term, you get this here. And if you plug it in here and here, you actually get the condition, the ratio test condition, that the absolute value of x has to be less than 1 for the series to converge, right? Converge to its original function and not diverge. The ratio of radius of convergence is 1. The radius is a circle, right? Circle, and its radius is 1, and this is 1, 1. So the length is 2, but the radius is just 1. You can get the radius of convergence, which is 1. And next time we'll see more in depth why it has to be that way, why it is a radius and not just length of convergence, or just the condition of convergence, but the radius of convergence. Why is the radius? Where is the circle, right? There's no visible circle you can see intuitively, but on the next video we'll talk about the circle and the radius of convergence. Thank you.